Welcome, ladies and gentlemen, to a talk on spatial data analysis as decision support aimed at the improvement of agricultural fertilization strategies. This is a report on ongoing project, work in progress, so to say, and we are happy to present some ideas and some first result on the International Conference on Advanced Geographic Information Systems, Applications and Services. So I would like to introduce briefly the StaPrax Regio project within the framework of this talk. The main theme is nitrogen fertilization in agriculture, and from some basic information, the work process in StaPrax Regio will be explained. Anyway, data play a very important role, and we will see that data come from different sources, and this data has to be integrated, has to be prepared for GIS analysis. And due to the fact that much data is based on point measurements, spatial interpolation plays a role as well in the field of GIS analysis. Last but not least, much data can be visualized because it's spatial data, and we developed and implemented the StaPrax Regio map server as a specific tool at the moment for the partners within the project, but as a forecast in future, such a map server could be helpful for many people outside our project. Well, the StaPrax Regio consortium is situated by different partners. The project lead comes from industry. It's a SKW Piesteritz Limited, so to say, in Kunnersdorf, Leipzig, a producer of nitrogen fertilizers, of inhibitor-based nitrogen fertilizers. There are two partners from administration, States Agency for Environment, Agriculture and Geology of Saxony and the German Weather Service. And myself, I'm from Harz University of Applied Sciences, and I'm happy to comment this video. However, the whole project is based on collaborative research, which shows also that the industrial partner is doing scientific analysis and research. They have a specific scientific department there, research department, as well as the administrational partners, because the States Agency for Environment, Agriculture and Geology, as well as the German Weather Service, of course, they are collecting data, but they are also analyzing data and providing data in processed formats. The goal of the StaPrax Regio project is the optimization of fertilization strategies, and this is important under consideration of meteorological and edaphic parameters. The part of the analysis and visualization of data using GIS is more a supporting part within the project. And as you see, there is weather data, there is soil data, and there is data from different fertilization practices on different fertilization practices from different test sites. There are more than 80 test sites spread over the country, from the north to the south, from the west to the east. And here the weather conditions, the edaphic conditions are collected, and different combinations of nitrogen fertilizers. So the data coming from the test site is comparable. It's a proper scientific data collection procedure that happens there, and this data is quite important together with the other data sets. Only some words on nitrogen fertilization, because this plays the main role within the project. And I choose the title Curse and Blessing here, and I will show using two citations that indeed nitrogen fertilization can be seen as curse and blessing. In the first citation, you can read that, of course, nitrogen is the most essential nutrient in crop production. but it is also one of the most challenging to work with. The compound is central to global crop production, and particularly for major cereals. But while many parts of the world do not have enough to achieve food and nutrition security, in others, excess nitrogen from fertilizer leaks into the environment with damaging consequences. Curse and blessing. There is a second citation, and I took this from the report from the Commission to the Council and the European Parliament. Nutrients such as nitrogen are essential elements for the plants. They are often used as fertilizers in agriculture to guarantee higher yields and quality products. We know that well since many years. And without nitrogen fertilizers, it wouldn't be possible to feed the world population. But again, there is a but. However, the increasing demand in food production has resulted in an increased production and use of fertilizers, associated with considerable inefficiencies, leading to pollution of water, air and soil, affecting human health and the environment. So these losses, these inefficiencies, this is a central theme within the framework of StaPrax Regio. This is somehow summarized in this small image here, which shows us, well, when the fertilizer gets on the ground and gets into the ground, not the whole amount of fertilizers is taken up by the plants. Only those parts that get into the crop root zone can be taken up by the plants, whereas another part is contributing to air pollution to a certain amount and can pollute groundwater, water, soil as well. So when we speak about the optimization of fertilizing practices, we have to take into account not only the amount of fertilizer that gets on and into the ground, we have to take into account some other parameters as well, edaphic parameters, soil type, and many criteria and parameters that describe soils, as well as the meteorological conditions under which the fertilization takes place, days before, days after, and so on. So considering the environment conditions is a very important issue. And of course, the fertilizers themselves play a role because there are different kinds of nitrogen fertilizers, and inhibitor-based nitrogen fertilizers have become increasingly important in fertilization. An inhibitor is a compound added to nitrogen-based fertilizer to reduce losses when the fertilizer has been applied to the crop. And I wrote reduce in bold because this plays, again, this very important role. And let's look on the second aspect here. Nitrification inhibitors prevent bacteria in the soil from converting the ammonium portion of nitrogen from the manure into nitrate. And this reduces the risk of the nitrate leaching and denitrification, both of which remove nitrogen from the crop root zone. And the crop root zone, as you see in the small image on the right side, plays, of course, an important role because only the fertilizer that stay for a certain time in the crop root zone can be taken up by the plant, whereas another amount, as we saw before, is emitted into other directions, the atmosphere, deeper soil levels. The project lead, SKWP, is producing inhibitor-based nitrogen fertilizers, and two of these inhibitors, MPA and 2-NPT, you see them in this image on the left side. They influence the enzyme urease and it blocks the active center of the enzyme, and this has consequences. It works as long as the fertilizer does not penetrate the soil or only insufficiently. It delays the hydrolysis of urea, which is a quite important process as well, and this leads to significant NH3 minimizations plus improved nitrogen distribution in the crop zone. So the minimization of NH3, ammonia, and the improved nitrogen distribution in the crop root zone. This is something that follows when we are fertilizing with inhibitor-based fertilizers, and this results in the idea that inhibitor-based fertilization under explicit consideration of weather and edaphic information will lead to more sustainable fertilization strategies. This is a kind of hypothesis of the project, and we are still struggling and discussing this hypothesis, and from this results a work process where we have 3 general phases. Of course, we have a much more detailed work plan within the project, but this general aspects is data collection and GIS analysis of the data, is the identification of relevant criteria and the search for potential weightings. Are all the relevant, all the criteria equally relevant, or are there some criteria more, others maybe less important? This is a quite important question. And from this, maybe models can be developed. Spatial patterns can be identified where the GIS component again plays an important role. And those spatial patterns could lead to recommendations concerning fertilization. Are there regions within the country where specific edaphic parameters and specific weather conditions can influence a specific fertilization strategy, so to say. Anyway, where comes the data from? I spoke about the test sites. Here you see a nice summer situation close to the Stickstoffwerke Piesteritz, SKWP in Kunnesdorf, and you see test fields. On those test fields, different crops are growing, and they are fertilized with different combinations of fertilizers, and now you can collect the data on crop yields, for example, and this results in analysis as you see them here. For one test site, on the x-axis you see different combinations of nitrogen fertilizers, some of them inhibitor-based, and on the y-axis you see the yield, the crop yield, and of course differences are observable, and if we now take into account the edaphic parameters, the weather parameters, in combination with this data, one can interpret the data in terms of, well, why do we have on a specific site better results concerning crop yield, whereas we have on other test sites not so good crop yields, even we tried the same combination of nitrogen fertilizers. So the interpretation, the analysis of this data and the interpretation of results leads to insights that play a role concerning our goal to optimize fertilization strategies. Weather data is coming from the German Weather Service. The Weather Service has an open data server, which is quite nice, and you can access many different data sets. Only 2 examples here: soil moisture under grassland, or the aridity index, and many more on weather parameters. Soil data is needed, and you can access digital soil data at many places. mostly provided by the state's agencies for geology. And those data flow into the data bases. You see here one example of a table provided by SKWP, test site related data. And underneath you see a table where we integrated all this data, test site data, soil specific data, of course weather data can be added, and based on such an integrated database you can apply a geographic information system. Well, due to the fact that much of the data has been measured point related, we have automatically to discuss spatial interpolation as a means to come from point related information to field related information. Spatial interpolation methods, there are different spatial interpolation methods, and it depends from the distribution of the point related measurements which interpolation method could be used or is suitable for our purposes. So the distribution is not a regular one, as you see it in situation B here. Probably it's more between A and C. And we looked for an adequate interpolation method and came for the first step, in the first step, to a very classical one, so to say, ordinary kriging. And due to the fact that we use only open software, we use QGIS as a geographic information system and an extension, Smart Map, that you can find in the QGIS Python plugins repository, and Smart Map provides ordinary kriging as one method. To interpolate spatial data, you see also machine learning approaches, and we will discuss for the next period if, apart from spatial interpolation method, maybe other approaches can be chosen as well. So the workflow to apply the ordinary kriging method under consideration of the data provided by the different partners and so on is presented here. And based on this workflow, we are interpolating different data sets. And as a means to provide the data to our project partners, we implemented the StaPrax Regio map server. Some few technical issues you can read there. Based on this map server software, it is possible to provide spatial layers via standardized OJC-conform web map services. You see an example here, and many different data sets have been included here, and all the partners can access the StaPrax Regio map server, where we have now the weather data, the soil data, the results of interpolation of data, of test site data, and so on. So this is an example, ammonia loss potential, where you can get all the data for each pixel in this map. This is another example, the usable field capacity in the root zone. We learned already the root zone, yes, that's quite important. The crosses you see are different soil measurement points, so to say, and you can access again the usable field capacity here via the map server. Integrating of data, of course, is an important issue, and the classic overlay with GIS can lead to new insights. Yeah, like you see here, the soil moisture under winter wheat, which is a crop that is grown here. So yeah, you can combine the crops with weather and edaphic data. Or here, another example where you have information on precipitation, on soil moisture, on the soil type, and again the culture, the crop culture that is grown here, and you see patterns, you see different regions, and now you can start to interpret this data again. So, as I said, this is work in progress, and here I would like to give some conclusions. Well, the data collection phase is finished in the sense of we have all the means to provide the data. Of course, new data is still collected at the test sites. Interpolation is a central analysis method, so to say. The weather service delivers also interpolated data, but the point measurements have to be interpolated to achieve field-related information of test sites, and currently we use ordinary kriging here. The classic GIS overlay of different data layers leads to new insights. The map server provides this data, and we are able to try out new combinations. And based on this work, we can go a step further to achieve the overall goal to identify spatial patterns of similar conditions concerning the dependence of weather and edaphic data under consideration of specific fertilization procedures. So we try to set up a more holistic perspective on fertilization with nitrogen fertilizers. And if it is possible to identify such spatial patterns and visualize them via maps, this can support decision making in agricultural fertilization. So the StaPrax Regio map server can be an important means here, can act as a decision supporting tool, but we want to go a step further, of course, because providing visualized spatial patterns can be even a better decision support. Maybe, hopefully, combined with recommendations of a suitable fertilization strategy independence of the different regions. Yes, so this is the end of this brief introduction to this ongoing project. Thank you very much for your kind attention. I had the opportunity to speak about this project. Of course, there are experts from the Weather Service, from SKW, from the State's Agency for Environment, Agriculture and Geology. If you want more information, more detailed information, please feel free to contact all these partners. And at the end, I would like to do an acknowledgement. The project is funded by the State's Agency for Agriculture and Nutrition of Germany. So the hope is that maybe at the next international conference on advanced geographic information systems, application and services, we can bring more results that go into the direction of the project goal. Up to now, we are at this stage. Thank you very much again, and goodbye.